Time for chapter 26. So we're going to talk about the discovery of galaxies and, why we used to call them nebula or spiral nebula, and how it is that we figured out that these are galaxies. So, story time. April 26, 1920, the National Academy of Sciences was having their annual meeting. Two different scientists presented papers on the scale of the universe, and they had completely different suggestions on the scale of the universe and how that relates to spiral nebula. So remember Shapley. We talked about Shapley last week. He was the guy who used globular clusters to figure out the size of the Milky Way galaxy. Shapley thought that spiral nebula were relatively small and fairly close by within the Milky Way galaxy, scattered about small structures. On the other hand, Heber Curtis, University of California's Lick Observatory, had this idea that the spiral nebula were actually very large and very far away, rotating systems of stars like our galaxy. So, as happens at most scientific meetings, during the day, and different people give their presentations, and then in the evening they usually get together again and just chat, and everybody talks. And so at this meeting, 1920, they spent a lot of the evening discussing these two different ideas on spiral nebula, and not a thing was decided. Why is that? Well, the reason is that no one could give a good idea how to figure out how far away these nebula were. So we're going to move on for the moment, but we will come back to that in just a minute. So in the process, we're going to talk about the properties of elliptical, spiral, and irregular galaxies, and do those properties change over time. So this is an image that shows us Hubble's galaxy classes. Hubble looked at hundreds of thousands of images of galaxies and broke them down into three groups, and then a catch-all fourth group for anything that didn't fit. So Hubble had spiral galaxies, barred spiral galaxies, and elliptical galaxies. So we're going to start with ellipticals. Ellipticals have no structure, no arms. There is sometimes, often, a central bulge, a rounded portion beyond that, and that's really all. Hubble classified them with an extra either 0, 1, 2, 3, 4, 5, 6, 7 based on how round or flat they looked. So, very round is an E0 and extremely elliptical is an E7. We do find, here is a particular dwarf elliptical. This is M32. And it is one of the companions to the Andromeda Galaxy, M31. And so, all spheroid, no disk, no arms, just a bunch of stars. That's basically what ellipticals are. Compared to that, we have spiral galaxies. So in spiral galaxies, we have these arms that come in and spiral into the central bulge. If we turn spiral galaxies and look at them edge on, the disk is those arms, except, we're looking at it from the side, so all we see is the disk. So a couple of things to notice. Once again, we have the central bulge. In the disk, all of that dark part is dust in the plane of the galaxy, in the spiral arms, and we can see it because dust absorbs the light from the stars in the galaxy. So already we know a lot about galaxies. Spiral galaxies have stars in arms, and the arms include a lot of dust. There's a central bulge. The halo around the galaxy is mostly globular clusters and very little dust. So we already know a bunch. Hubble classified spiral galaxies according to the texture of their spiral arms and the size of the central bulge. So spiral A galaxies have broad spiral arms and large central bulges, and so the spiral arms are fairly wide. Spiral C have much narrower arms, larger spaces in between, and smaller bulges. B is sort of the in-between state. So barred spiral galaxies have this bar of stars that seems to cross the central bulge, and the arms extend from that. So NGC 1300 here really only has two arms, and they begin at the ends of the bar and spiral out. But barred spirals are, they're just a subclassification, well, not a subclassification, a distinct group of spirals. So central bulge, arms, disk if viewed edge on, and the halo. So once again, same classification. Classified based on the arms and the central bulge. Small central bulge, narrow arms, lots of space in between for the C group. Fuzzy, wide arms, not much space between them, and a large central bulge for the A group. And the B is sort of in between. This has a larger arm and, space in between. So, and then irregular galaxies were everything that Hubble couldn't put into one of those other three. There really aren't a whole lot of irregulars. We do need to remember that there are dwarf and giant for, both ellipticals and spirals. Giant ellipticals are quite rare. Dwarf ellipticals are very common and very transparent. It does not look like a nice compact central bulge. Dwarf ellipticals are very transparent and hard to find. We didn't really start finding dwarf ellipticals until the last 5 years. So Hubble believed that galaxies the stars within them would move around over time, and that they would evolve from one type to another. We have since figured out that that is really not the case, that what happens instead is collisions. And so we see collisions in between two galaxies. I showed this picture last week. This is one of my favorite galaxy collision images. This is called antenna galaxies. And this is two separate galaxies that are colliding. The picture here shows streams of stars being left behind, but because we know that blue stars in spiral nebula, which we're about to learn are galaxies very far away, blue stars are often younger. And so as these two galaxies are colliding, it's creating a compression event that is causing all of this star formation. So we're also going to look at, how do we figure out the mass of a galaxy? So if we are looking at a galaxy, we do the same thing. Remember Kepler? I said we would keep talking about Kepler. Well, we do the same thing. We look at how quickly these stars in the outer region of the galaxy are moving around that galaxy. Use Kepler's third law to figure out the distance to the center of the galaxy, add in Newton's physics, and we can calculate how much mass is necessary inside that orbit in order for this particular clump to move at the rate that it is moving. So we can figure out the mass in spiral galaxies. Ellipticals, not so easy because it's harder to find a specific star and watch it move. Now on ellipticals we can zoom into the central portion of the galaxy and watch the central objects move around the core. And it gives us an idea of the size of the central object that would be necessary in order to make the stars move at the rate that they're moving. Doesn't necessarily give us a great measure on the mass of that galaxy. We have to, do the same thing. Go as far out as we can and observe a star moving. Measure the distance to the central object and then estimate that mass. So looking at the galaxies by type, if we compare them to the mass of the sun, spirals, ellipticals, and irregulars, we notice that ellipticals can be both the smallest and the largest galaxies out there compared to the sun. Diameter, no great trends. Luminosity, no great trends. Population. So ellipticals are almost entirely old stars. That will be interesting. How would we figure out how spirals that have old and young stars relate to ellipticals with only old stars? So we're going to come back to this idea of collisions. Interstellar mass. Well, remember that we talked about the interstellar medium and that it is gas and dust. On ellipticals, there's almost no dust and very little gas. This relates to the fact that the stars are old and there is no star formation occurring. The gas and dust in the interstellar medium on spiral galaxies means that as those continue to age, they may that gas and dust can collapse into new stars. So just some interesting pieces to help us build this puzzle. And then, how do we use the variable stars to estimate the distances to galaxies? Well, I've been talking 14 minutes and this is a bigger section. So I'm going to go ahead and pause here and start a new video. So I'll see you in just a minute.